Okay, folks, so you can continue answering the survey while we get started. So, the first question. For an aerofoil, what do we call the line that traces the average shape that's equidistant between the upper and lower surface? Is it the chord, the leading edge, the trailing edge, or the camber line? And 71% of you said the camber line, 21% said the leading edge, 7% said the chord, and none of you said the trailing edge. So I do give you credit there. Someone put trailing edge, please? No, I'm just kidding. It is the camber line. And if we go back to our diagram of the aerofoil, we have the leading edge, the trailing edge, and they are literally named that because the leading edge is the first part of the aerofoil that the flow sees, and the trailing edge is the last part of the aerofoil that the flow sees. And then we have our upper and lower surfaces as such. The distance, linear distance from the leading edge to the trailing edge is the chord, or little c. Because there's big C's too, but we use little c for chord. The camber line is that midpoint. And it's that curvature of the camber line that defines the basic shape of our aerofoil. And we've talked a little bit more about airfoils in the lecture and the like, and you'll know that there's a range of airfoils. The most famous families of airfoils are probably the NACA airfoils. You'll hear people call it NACA. It is not NACA. It is an initialism. It's NACA. It was the National Advisory Committee on Aeronautics, which was formed in the late 20s in the US and ultimately was merged with the equivalent committee on astronautics to form the National Aeronautics and Space Administration. But NACA, they did a bunch of studies. And their airfoils are really nice because you have 4-digit airfoils, you have 5-digit airfoils, and the like. And each of those types of airfoils mathematically describes everything you need to know about the airfoil. So a 0012 is a symmetric airfoil of 12% thickness. A 2412 is cambered. It tells you the shape of the camber line, the point of maximum camber in terms of distance from chord, and the thickness. And then also with some other functions, it'll tell you the radius of the leading edge and the like. And that went all the way up, and now we have NASA airfoils that were developed after NASA was formed and the like. There are also lots of other airfoils. Each manufacturer will have its own airfoils. So Boeing has its own airfoils. Airbus has its own airfoils. And they're often mediations or moderations of known ones, but they are of course, trade secrets. What is the point on an airfoil where the moment coefficient is independent of the lift coefficient? Is it the aerodynamic center, center of pressure, leading edge, or trailing edge? Now, 68% of you said aerodynamic center, 23% of you said center of pressure. And then there's always the residual leading and trailing edge, folks. Anybody know the difference between aerodynamic center and center of pressure that wants to shout it out? They are not the same thing. So one of them will be the question that we're asking today, and one of them has a very different definition. So you are right, the 68% of you, that the aerodynamic center is the point where the moment coefficient is independent of the lift coefficient. That means as the lift coefficient goes up, the moment stays the same. But that moment does not have to be 0. If the moment is 0, what point on the airfoil are you at? Center of pressure. Center of pressure is where all of our pressure and forces resolve. So by definition, if they resolve there, the moment is 0. You just have pure forces. You have pure lift, pure drag. Same thing happens with shear, and we tend to lump it together. Now, the center of pressure is an evil thing. It moves as we change angle of attack. And in certain situations, it's not even on the airfoil. If I have an airfoil giving you a nose-down pitching moment, wanting to turn down, generating 0 lift, where is the center of pressure located? So it's nose down, generating 0 lift. To get nose down, if I have a force, if I define lift as positive up, we'll use up in this case, I need it to push up. But of course, it's generating no lift. So where does that have to be located? Yeah. Somewhere behind, infinitely far behind of the airfoil. As in, it's gone all the way around the world and come back again and done it again. If I have an airfoil producing 0 lift that has a nose-up pitching moment, it will be infinitely far in front. Okay? So it moves. It's evil. That's why we don't use it. The aerodynamic center, on the other hand, tends not to move. At least not at one specific flight regime. I can change my angle of attack instantly, change my CL instantly, and it stays the same place. Where it does move is as we change speed. Specifically, as we change speed relative to the speed of sound. So does anybody remember where the aerodynamic center typically lies for an airfoil at low speed? In what we call incompressible flow, where Mach number is much, much less than 1. Yes? Quarter chord. Does anybody remember where it tends to migrate towards as we get closer to Mach 1 and above Mach 1? Yeah. About half chord. And it's not exactly at any of those places. The quarter chord is probably a more robust location. But what that means is that an aircraft that is designed to fly at Mach 0.2, 0.3, i.e. a Cessna, if you then, for some reason, magically accelerated it up to, say, Mach 0.85, it would be a very different aircraft to control. And there's a phenomenon we get in real aircraft as we accelerate towards the sound barrier, and it's called Mach tuck. And what happens is I've configured my aircraft, I've trimmed it for flying at Mach 0.3, I accelerate, that aerodynamic center moves aft, the neutral point of the aircraft then moves aft. Now, we're not generating enough downforce on our tail, or maybe too much upforce depending on the design, and the nose begins to push down. It goes into a dive. And we saw this in early high-speed commercial, what we call transonic commercial transports. The 707 was notorious for suffering from Mach tuck early on, and it required active control on the part of the pilots, to the point that it almost caused several severe accidents. We now have auto-trimming stabilizers. It's part of what's called the speed stability system in something, or the speed trim system. As we accelerate, the plane actively trims to keep the nose level, keep the speed at what we want it to be. Okay. Question 3. Which properties are true for symmetric airfoils? Now, symmetric airfoils are nice. They're very easy. They're also not particularly useful for a lot of things, but they're easy. The aerodynamic center and the center of pressure are co-located. 81% of you said that. Works equally well upside down. 65% of you said that. Produces lift at 0 angle of attack. 39% of you said that. 26% of you said had no pitching moment, and 3% of you said it doesn't stall. Now, the thing about a symmetric airfoil is its camber line is straight. It's coincident with the chord. That means there is nothing in the shape to turn the flow at 0 angle of attack. So by definition, it can't produce lift at 0 angle of attack. But also what's nice about that is because it's not producing any lift, it's not doing any turning at 0 angle of attack, we know it's also not producing any moment at zero angle of attack. In fact, it doesn't produce a pitching moment on its own at any angle of attack because it doesn't change the shape. The lift distribution is equal across the airfoil. Therefore, the aerodynamic center and the center of pressure are co-located. That means within reasonable flight ranges, not post-stall, that the center of pressure doesn't move. Now, why is this a good thing? Why might you want something that doesn't move the center of pressure with ranges? Where might you want something like that if you're not going to do any more sophisticated control? Works really well on something that sticks up on the back. Because you're not getting any moments while you're flying normally. Yeah. Yeah, the vertical stabilizer, the fin. We tend to use it also, at least on smaller aircraft, on the horizontal stabilizer, because we want that control. We then tend to bugger that up by having flaps that change the camber. And some horizontal stabilizers, especially in commercial transports, are actually cambered. They're just flipped upside down. It has no pitching moment. Now, doesn't stall. It takes a lot more complex stuff not to get stalled. That's a much higher, more complex flow field. It's not something we see in 2D. So they all stall in 2D. We'll talk about wings here in a second, and then we'll talk about not stalling. Okay. A normal cambered airfoil, that's one where the arc just goes up, has what type of pitching moment? Nose up, nose down, or none at all. And 65% of you said nose up, 26% of you said nose down, and then 10% of you had none at all. It is nose down. This is very important. So a normal cambered airfoil, which produces positive lift at zero angle of attack, or you could also say its zero lift angle of attack is below zero, because of the shape, produces lift aft of the aerodynamic center, and therefore will produce a nose-down pitching moment. Now, the dependence in the way we do that shape will change that. What it means is it's not very good for what type of aircraft? Where would you not want something that produces a nose-down pitching moment? Yeah. Not necessarily. Talk about its type of configuration. If we are missing something, where would it be bad to have just to always have a nose-down pitching? Yeah, if you don't have a tail. So tailless aircraft, we don't want to use normal cambered. The bigger the camber, the more downforce we need on the tail to correct it for a given static margin. So we have losses there. The bigger the camber, of course, the more lift we generate at low angles of attack, which might be really nice. Okay? So, the next one is a supercritical airfoil. Which of these properties are true? Delays the onset of supersonic drag. Lift generation is aft-loaded, has a higher critical Mach number, less nose-down pitching moment, and develops weaker shocks. Now, anybody remember what the other name for supercritical airfoil is? It's also known as a Whitcomb airfoil, after the guy that actually first properly described one. But there's another name for it that describes the lift distribution. If I put up the right answers, maybe that'll jog your memory. So for supercritical airfoil, the lift distribution is aft-loaded. So these are supercritical airfoils. And the way you notice them is if we look at the very back of the airfoil, we tend to have a lot of curvature, but we have a relatively flat upper and lower surface. And if you ever fly generally a low-cost carrier and you board from the ground where you go up the stairs and you have to board from the rear door, you tend to walk around the wing. Look at the trailing edge of the wing on your A320 or even your 737s, and especially if you fly on, say, a 787 or an A350. If you look at that trailing edge, you'll see there's a lot of curvature in that trailing edge, and that's because they have supercritical airfoils. Now, what that means is if I draw the camber line on this one here, it's pretty straight through here, and then gets a big curvature at the end. Remember, the big curvature in our camber line is where we generate our lift, so we're aft-loading our lift. And what that means is that we get very little difference in forces here and a lot of difference in forces there. What do you think that does to the pitching moment? Will that make it more nose up or more nose down? If I generate a lot of lift at the back of the airfoil, what's the airfoil going to want to do? Yeah, more nose down. So it generates, it makes that worse for all of its benefits. But the nice thing is, because I'm not generating a lot of lift here, I don't have to accelerate the air as much. Remember, to generate lift, you need a pressure differential. To get a pressure differential, the air has to go faster, the fluid has to go faster. And to do that, we're getting closer and closer and higher Mach numbers. And then when we slow that air down, the flow down at the back of the wing, we drop it back through Mach 1. What do we need to get back down from above Mach 1 to below Mach 1? If we did it infinitesimally small, we would get what? An infinitesimal change in speed and an infinitesimal change in pressure is what is called what? You're listening to it right now. It's called a sound wave. We have a finite step change in pressure, we get a shock. The bigger that step change, the stronger that shock is. One of the things about shock waves is they generate entropy, i.e. losses, drag. So by delaying that and making it as small as possible, we get less drag at a given Mach number. What that means is that we've delayed the onset of supersonic drag. So we have aft-loaded airfoils, more nose-down pitching moment, weaker shocks. What we don't do is we don't change the critical Mach number. Because that airfoil, that same thickness of airfoil, it will have flow. The flow over it will go supersonic at exactly the same speed as a normally shaped equivalent airfoil. So if it's Mach 0.74, it's Mach 0.74. But instead of having what we call Mach drag divergence, where those shocks start forming and they get strong and the drag goes up exponentially, instead of that occurring at, say, Mach 0.75 or 0.76, we may delay it to Mach 0.8. We get more efficient use. So a supercritical airfoil has the same critical Mach number. It's just designed to operate at above its critical Mach number, unlike a standard. Okay? So that's this set of polls, or this survey. Let's go to Q&A. There's the wave. We'll get to the winglet one here after the next one. Any other questions anybody wants to ask before we move on? Okay. Well, let's open the wing survey. While you're doing the wing survey, if we want to minimize nose-down pitching moment, does anybody remember what type of airfoil we would want to use? So remember, in a supercritical airfoil, we get a lot of what we call positive camber, curvature that turns down at the end. We want curvature that turns up at the end if we want to eliminate that. And that's called a reflex cambered aerofoil. That's the wrong way. You can see my calendar. So we have a lot of camber up front to generate our lift, and we have a small amount of adverse camber at the back, generates a little bit of downforce, which cancels out that pitching moment. So if you're looking at a flying wing like B-2 or a tailless aircraft, you'll often see a little bit of reflex in that trailing surface. Now, we might do it with a control surface with a tiny bit of deflection, or we may build it into the wing. But that's how we get rid of having a tail. So the 22 of you answered. If someone else answered. Darn. It was spot on 50% until 2 more people answered. So we're on to 3D wings. Now, aerofoils are nice. They extend all the way around from one end to the other or to the walls. All sorts of nice benefits. They're easy. Unfortunately, they're not particularly useful for aircraft. Where on an aircraft might we see effectively 2D aerofoils? As in, they are infinite. They go from wall to wall. Yeah. Huh? In the middle? No. Very specific application. Not all aircraft have them. So it wouldn't be on a glider or on a Cessna 172. But it's on every commercial transport you fly. So wings, they end. There's an open space beyond them. Think of an airfoil shape that doesn't have an open space beyond it. They tend to spin. So if you take a compressor disc, take a compressor blade or a turbine blade out of a gas turbine engine, those are airfoil shapes. And they have a wall at each end. And they are 2D, or effectively 2D. They behave like 2D airfoils. Now, they are directly in the wake of the preceding blade and all of that stuff, so it's much more complex. But we don't have any of those things like tip losses and things like that. Okay, is the lift curve slope, or the lift curve slope of a 3D wing is greater than a 2D airfoil? True or false? And as of now, 57% of you put false, which is, of course, the correct answer. What we have in a 3D situation is we have a free end. And free ends, where the atmosphere is there, screw everything up. Sorry, guys, they make it harder. But one of the things they do is they mean that we get less increase in CL for every increment in angle of attack than we would if it was a cap end. We also get more drag, we get potentially span-wise flow, we get all sorts of weird things that go on with that. But the first and foremost is we get less lift for a given angle of attack. So the lift curve slope is less. A normal wing produces lift at its tip. True or false? And 68% of you put false, which is, of course, the correct answer. Now, why is this the case? It was supposed to go over, but it hasn't. There we go. Why is it the case that we produce no lift at our tip? Now, here's our wing. We're looking at it from either the leading edge or the trailing edge. That's the green lines with the arrow is what's called our span-wise lift distribution. And the reason it goes to 0 at the tips is the same reason that me talking to you doesn't generate entropy. can do it forever. Not the sound waves themselves, obviously me generating it. We have a pressure differential between the upper and the lower surface. If you don't have that, you can't have lift, right? Turns out the pressure differential is caused by the generation of lift. It's the way we resolve that. It's caused by the way we turn the flow. But if I have a pressure differential here, so it's greater pressure here and lower pressure here, what happens? What do I get? Yeah. I can get a vortex, but what's it called if there's a high pressure over there and low pressure over there and I'm standing outside? What do I feel? I get wind. I get flow. Flow moves. And that flow moves to eliminate that pressure differential. So I have either choice. The pressure differential eliminates itself, in which case there's no pressure differential between the upper and lower surface of the tip, or it remains. To remain, I have to have a step change, because they're right next to each other. It's not a great distance. They are literally like this. That step change is called a shock. So unless I have a shock wave, that pressure differential has to go to 0. Now, the only time we can have a shock wave is where we have supersonic flow. You don't get supersonic flow between the upper and lower, supersonic flow differential, as in greater than Mach 1 speed difference between the upper and lower surface of the wing at the tip, unless you theoretically are flying faster. So what happens is flow will move from the lower surface to the upper surface, generating our tip vortices and canceling out that pressure differential. Without that pressure differential, we can't have lift at the tip. So it goes to 0. Now, that shape of that spanwise distribution, how smooth and gradual that change is what tells you, what gives you the amount of what we call induced drag. That's the drag due to lift. The sharper, the steeper that curve is at the end toward the wingtip, the more induced drag we get. So we want that shape to be as close to a perfect ellipse as possible. And actually a very eccentric ellipse, broad. If it's circular, very steep, much more losses. Okay? And we do lots of things to control that. We taper our wing. We increase our aspect ratio. We have wing tips and the like that do that. So, question 4, winglets. Winglets, the purpose of winglets is to improve that. They approximate a higher aspect ratio wing without which disadvantages? Is it without increasing the root bending moment, without decreasing structural stability, or without increasing span? And it's the first and the last. So a winglet is what we call non-planar surface. So instead of extending our wing out, we bend the tip up, or actually down. Believe it or not, down is more efficient than up. And by doing that, we increase that effective span because we give more time for that lift distribution to run out. But we're not generating lift further and further away from the root. Remember, in a cantilevered wing, if we generate more force further out, we increase the bending moment. And we're not increasing the span as much as if we went further out. It isn't as efficient as doing that as a pure increase in distance. So if I have a winglet that's, say, 2 meters tall, the benefit I get isn't as good as having 2 meters of wing extension in terms of absolute drag and lift over drag ratio. But I don't have to worry about, say, my wingtip hitting another aircraft on the ground or a light pole, because it does happen, or increased root bending moment. One of the downsides in winglets is that they decrease the structural stability of your wing. They make your wing want to rip itself off. Because of the way they generate, they're out at the tip, they actually tend to generate nose-up pitching moment out at the tip. It's behind, thing bends, wants to do that. So what they tend to do, most manufacturers when they put winglets on an aircraft, is they stick weights on the nose, on the leading edge. They put literally hunks of tungsten. to stabilize the wingtip. Now you can do some fancy aerodynamics and get away with that. Embraer on the original E-jets did that. Now, upward or downward facing winglets are not the only option. We see them a lot. You see on the 737, next gen, they had what were called blended winglets. You have the sharklets now on the A320. Older A320s didn't have winglets. What did they have? Yeah, they called them wing fences. They were these little triangular things. You still see it on the A380. And they gave some benefit there, not as much benefit as a full winglet, but they didn't have the interference drag that winglets had. So when I started working for Delta Airlines back in 26 years ago, we had several 727s that we had retrofitted with winglets. And it turns out that for our typical mission at the time, their aircraft burned more fuel than the ones we didn't retrofit with. And the reason why is Delta at the time flew 727s from Atlanta to Macon, Georgia, a grand total of 60 miles, so 100 kilometers. We also flew them Birmingham, Alabama, because it's not pronounced, which was 100 miles. And we flew them a bit further, but most of our flights were short-ranged. And the winglets really only came into their own at the extreme range of the 727. And it was because the design of the winglet, how the winglet joined the wing, there was what was called interference drag. And we just didn't have the computational capability or the experimental resource to get that perfect. A few years later, they came out with what's called the blended winglet. So you'll see a nice swooping change, which is what you saw the sharklet and the like are, and that reduces the interference drag. And that works really well on things like 737s and A320s because their wings are almost already at the limit for what's called code or category C, the gate spacing limit, ground limit. And it turns out that most airports are designed to have a lot of those stands and a lot fewer stands for larger aircraft. So it makes a lot of sense to put an upward-facing winglet on a 737 or an A320. A few years later, Delta went to Boeing and Airbus and said, we need an aircraft to replace our L-1011s, which was this magnificent tri-jet built in the designed in the late 60s and early 70s, competed with the DC-10. Not quite as magnificent, though the DC-10 actually made money, and the L-1011 lost Lockheed its shirt. But that's Lockheed. And we need it to fit in the same stands that the L-1011 did. Now, the L-1011 has a relatively low aspect ratio wing. The 767 and the A330 have higher aspect ratio wings. The problem was L-1011 fit in a code or category D gate stand. The A330s are category, and like the 777s and the 747s, are code E. So what Boeing did is they started looking at winglets for the 767. But they had some space to grow because the 767 wing wasn't big enough or wasn't so large. And they did a bunch of tests, and they looked at doing winglets. But they also looked at, instead of having a non-planar, what happens if we sweep the tip? Maybe turn it up slightly and back like that, and much higher taper ratio. And they found for that configuration and for the operations they were looking at doing was actually more efficient. And you see that today on 787. It's more advanced. You see it on the P-8 Poseidon military 737s. Because of the combinations of operations, it turns out that's more efficient. Airbus looked at the similar thing on the A350, and instead of having straight up sharklets, you have much more gently raised and swept back winglets on the A350. So there's all these combinations. Now, the next question. If we want to decrease drag at high speeds, as we're getting closer and closer to the speed of sound, what do we typically do? Do we sweep the wing? Do we use aft-loaded or supercritical airfoils, or do we decrease the thickness to chord? And in actuality, the answer is we can do all three. Now, when we sweep the wing, we change the normal speed. Because we've swept it back, the normal velocity is lower, so we can fly faster to get the same Mach number over the wing. If we use aft-loaded airfoils for the same Mach number over the wing, we get less drag. At the same time, if we make our wing thinner for the same Mach number, we get less drag. The benefit of a supercritical airfoil is that for the same sweep, we can use a thicker wing. The reason that's nice is it does better for lift at low speeds, so better takeoff and landing. And what else is nice about having a thicker wing? Yeah. We can hold more fuel, and one other thing. The wing is thicker. What does it make it? Yeah. It makes it more strong, has better stiffness. It makes it lighter. We don't need as much material to get the same strength. So our wing is lighter, it holds more fuel, and that's the trade. Okay. It is, oh dear, we're running out of time. There is one question before we move on to the next survey, and the last survey on this one. If winglets are beneficial to aircraft as it changes the direction of the wingtip, why does this 777 fold its wingtips at takeoff? 777X actually has folding wingtips that go down at takeoff. Those non-standard wing extensions, the swept wingtips. The reason they fold them up on the ground is because with those wingtips now we're in a code F aircraft, which there are a lot fewer code F than there are code E stands. So it can fit into the same stands as an old 777, but yet gets that efficiency. Now, the original 777 design had folding wingtips. They were much more aggressive, heavy, and complex, and no one bought them, and they were eventually removed from the design, but they were there. Okay, last survey on flaps and stuff, and we'll quickly get through this. If you have an answer, do you believe that the 70% who have said true are correct, or the 30% who said false are correct? So just remember, all a flap is a surface on an airfoil or on a wing that changes its camber by moving up or down. So by definition, an aileron does exactly that. We change the camber, we change the lift distribution at that point, and we can therefore roll the aircraft. So they are a type of flap. Now we don't call them flaps in general parlance because we talk of flaps as being things that are specifically there to change the maximum lift coefficient of our wing or the drag or both. And these are about control. But they are flaps. And we can do flaperons where they're both overall lift generation and roll control. And the like. Okay. Which type of trailing edge flap increases the effective wing area? Is it a Fowler flap, slotted flap, plain flap, split flap, or Kruger flap? And the right answer was what 39% of you put, is the Fowler. The Kruger flap is a leading edge device of a specific type, and we'll talk a little bit more about that. Plain flaps are like standard ailerons. They just bend up or down. A split flap literally splits the wing by bending down. You don't see them very often. They use them on the B-52, certain versions of the B-52. A slotted flap gets a slot, and a slot allows high-pressure air to come from the lower surface onto the upper surface, and it helps increase the angle of attack at which it stalls. But a Fowler motion literally is that translating motion aft that increases the wing area. Now, most aircraft that you see today commercial aircraft have a combination of slotted Fowler flaps. So they're slotted, maybe single, double, or triple on some older aircraft, and they have Fowler motion. And as you watch, when they extend the flaps, the first thing they do is move aft, and then they move down. The A350 and the 787 are a little different. They don't have much Fowler motion. They just tend to move down and open up that slot. That means they're lighter, all else remaining equal. Okay. What type of leading edge flap does not increase the angle of attack for stall? Is it a slat, a split flap? Not going to be that. That's a trailing edge one. Kruger, a slot, or Fowler. Now, the thing about flaps of all sorts, unless we put a slot in, they actually decrease the angle of attack at which stall occurs. Because they're turning the flow more, there's more likely to get separation. So anything that doesn't have a slot will decrease the angle of attack. This is trailing edge, but if it doesn't have a slot, we'll do that. Kruger, leading edge, doesn't have a slot. It doesn't increase the angle of attack at stall. A slat literally means a slotted leading edge flap, so it has that slot increases the angle of attack. So it's that Kruger flap. And that's really nice. And we used to use them on swept wing aircraft because aft swept wings have a tendency to stall at the tip first and the root last, which isn't very good. Or in some cases, the tip stalls, but the root never does. And all of a sudden, that means the aerodynamic center moves and the neutral point move forward. And they may move far enough forward that they move forward of the center of gravity, making the aircraft unstable. Or even if they don't move that far forward, they mean it's harder to know that the aircraft is stalling. You don't get a nice nose-down pitching moment. So we have to do other things. 737 MAX MCAS, for instance. A320 hard envelope protection, which when it goes wrong, noses your aircraft down. So slats and slots allow that angle of attack to increase for stall. Okay? And then last one on this poll. Why do we use leading and trailing edge flaps? Absolutely to increase the maximum lift coefficient. We almost never increase the lift to drag ratio. We do use them to increase drag and decrease field length. Now, when you look at the takeoff flap configuration and the landing flap configuration for most aircraft, the maximum lift coefficient isn't that different. The big difference is between clean and takeoff. Landing, it's all about increasing drag. For takeoff, it is that best compromise between lift coefficient and lift to drag ratio. For landing, we want drag. We want to be able to come down quicker and stop faster. So that's why we actually have these really, really high deflections at landing. It's not about lift, it does do a little bit of that, it's about drag. We want more drag. And that's especially true with jet engines where we always have to generate some thrust. If you have a propeller, you can feather it, but with jet engines, we can't do that. Okay. Are there any last questions before we go? Why in the diagram of a plane you showed us with the different parts labeled are the flaps closer to the body of the wing and just labeled flaps not specified? So if we just call something a flap, that tends to imply it's a trailing edge flap that's there for the purposes of lift generation and potentially drag at landing. It doesn't serve a control purpose like roll or pitch. Because ailerons are most effective when they're out at the tips, we tend to put those closer to the root. Just a factor of where the space is available. And that's why they're labeled as such. They are all technically flaps, but in that day-to-day parlance, when someone says flaps, they mean lift generation devices, not control devices. Okay? Okay, guys. Oh, you've gone a little bit over. I'm sorry. Thank you very much. And login is working again now if you want it.